So just now we talked about the potential refraction from a potential step, which is an interesting phenomenon. You cannot imagine it in the classical world. Here it is. You have a lower step than you then, but the step has some probability that to reflect the particle. However, this is another case, which means that here we have a particle have a lower kinetic energy than the potential wall. However, there are some probability that the particle can go through the wall. In classical world, you cannot imagine this either. So this case is a plug. So this is the you can consider the this when you play the ice hockey，就是那个冰上曲棍球的那个冰球 plug。Climb the hill. This is the hill made by ice. So you try to ignore all the frictional force because mechanical energy conservation is have some condition, which means that there are no loss in between. So we assume there's a ice hill, and this is a plug. So we assume that there are no friction force between the plug and the hill. So here we assume that the kinetic energy of this plug is lower than the top of this hill, which is UB, so that you can imagine the kinetic energy of the plug will convert to some of the potential energy, maybe going up to here. Then all the kinetic energy has been transformed to potential energy, but it has no further kinetic energy, then it will go back through. So it cannot go through this hill. However, in the quantum world, there is some probability that even though this one has not sufficient kinetic energy, there are some probability that it can go through the wall. So in this case, it's a little bit different. So there's a wall with a thickness L, capital L, and this is an energy. So that there are three segments of a wire. In the middle part, you have VB, which is smaller than 0, so that you have a step UB like this. And for this part and that part, B is equal to 0, so that UB for these two parts are also 0. This is the case for the barrier tunneling. 就是那个串穗效应。So here, also we need to assume that the E is the kinetic energy of the particle is smaller than UB, in here. So the wave function describe the electron can be found by solving the Schrödinger equation separately for the three regions. In the previous case, we only have two regions, but here we need to solve it in three regions. So one is the to the left of the barrier, one is within the barrier, and the third one is the right of the barrier. So actually, we need to solve the Schrödinger equation with UB is 0 at region 1. So this is region 1, this is region 2, this is region 3. So for region 1, U is 0. Region 3, U is also 0. So as before, we can solve the wave function in the region 1 like this with both directions, because there are some probability that the electron will be reflected by the wall. But for region 3, we discard the negative direction term, similar to before, because if the particle can really go through, we don't really expect it will be reflected, because the potential is 0 until up to the infinity. So we don't expect the negative term similar to the previous case. We only have one term here. But for the middle one, it is a little bit different because we have u equals to ub, u equals to ub like this, and also we assume that E is smaller than ub, which means that the kinetic energy of the electron is smaller than the potential energy for this wall. So that this one is negative, this is positive. So the whole term is negative for region 2. So you can imagine B is defined something. B here is defined something like this. So here we have actually defined d square x d square something like this. B sorry, should be minus minus b square phi equals 0, because this one is a negative term, so that we can write it as a negative times a square number. This one is b square is always positive, or at least 0, but E is not equal to u, so E is not 0. So b square is a positive number, so minus b square is also always negative, and this one is negative, so it's okay. And here we just trace the order, so that ub is larger than E, so that within the square root it is positive, so that we can take the square root. It's not a complex number, it's not an imaginary number. So here they are a little bit different. For region 1, it is a complex sinusoidal, but here it is exponential function. This is also complex sinusoidal. So similarly, we also need to guarantee that the wave function at the boundary x equals to 0 and x equals to L to be continuous for the wave function and the first derivative of the wave function, so that we will have several equations to solve. And finally, writing these 4 equations, we can know the relationship between the A, B, C, D, E. Actually, E may not be a good value here. Maybe we should use F, because there is already E here. So that maybe this E should be changed to F. Otherwise, this E is conflict with that one. You may confuse. So this one should also be F, then the variable is not conflict with each other. So in this case, we only consider the transmission coefficient, which means that we calculate the probability that phi 2 at L over the phi 2 at 0, which means that we consider the particle can go to this surface, and the ratio to the particle go to phi 2, which means that the particle can go through this wall and then go into the region 3. So this is the probability stand for that one. The particle can really go through the wall, go through the potential wall, which has a higher energy than its kinetic energy. And it will be something like this. And actually, we need to make some approximation, because we have the term here. This one b is positive, so then c times exponential to bx will be exponentially increased. Although this term is not necessarily 0, but it will be a very small number. Otherwise, the probability of the particle going through this wall will be very high, which doesn't really make sense. And actually, as long as we solve the continuous for the boundary, we solve the boundary condition, we'll find that phi x will look like this. Will look like this. So for the left-hand side part, it is a standing wave, and in the potential wall, it is exponentially decay until here. Then it will go outside, and this is a plane wave, so this is the absolute radius and square of this part will be a constant. But for this part, it is not really a constant. It will be a standing wave, because suppose you add suppose you add ikx plus b minus ikx, it will be turned into two terms. Let me think. And actually, will be something like b equals to a or minus a, something like this. If b is nothing but a, then it will be something like 2a cosine kx, something like this. If b is b is equals to a. However, if b is equals to negative a, it will be something like exponential. So it will be nothing but 2 over j a sine kx. So, and actually it will be the combination between them. So you will see that it will be a standing wave here. And actually, when you solve the boundary condition, you will really know the phase of it. So it will be something like a cosine kx plus phi, something like this. And you take the square root and square. So this term, take the square root and square, it will be something like 1/2 1 plus cosine 2 kx plus phi, something like this. So you will shifting upward. So you see that for the left-hand side part is a standing wave, and the probability in the potential wall is actually decay exponentially, and outside the wall it will be a constant, because it is only a one-directional plane wave. and taking the square root of it is 1 for the exponential term. So finally, here as c will be very small, so then approximately calculating the transmission coefficient will be nothing but substituting L into here and substituting 0 also into here. Then you'll get d times exponential to minus bl over d times exponential to minus b0. And the final answer will be exponential to minus 2bl, which means that b is related to h is a h bar is a constant, m is also a constant for a fixed particle, and actually ub minus e it is related to the energy difference between the kinetic energy and the potential energy, which means that if the energy difference between your kinetic energy and the potential energy are very large, then the probability that you can go through this wall will decay very fast. And another term which is related to this probability is the L, which means the thickness of this wall. If the wall is thinner, then there will be a higher probability that the particle can go through the wall. If the wall is too thick, then the probability will decay to 0, and then you will go back. So this is the barrier tunneling microscope 穿隧式显微镜 scanning tunneling microscope. So this one it tried to move a tip close to the surface you want to detect. So it tried to maintain the fixed distance between the tip and the surface. And if you can maintain the similar distance between the tip, between them, then the probability that the electron can go through it will remain constant. So you try to control this tip up and down and horizontally so that you can scan the surface that you want to observe. This is the fundamental concept of the STM, scanning tunneling microscope. So here is a sample problem. So suppose the electron have total energy 5.1 eV approaching a barrier height 6.8 eV. So E is smaller than UB, and the thickness L is 750 picometer. So what is the approximate probability that the electron will be transmitted through the barrier to appear on the other side of the barrier? So actually you need to calculate the probability that it can go through. So it is actually if you really need to understand the theorem is a bit difficult, but actually to calculate it is nothing but substitute all the value into the equation. So actually we have B equals to square root of 2m times UB minus E and over H bar. So it is 2 times 9.11 times 10 to minus 31, and this is UB 6.8 minus 5.1 times 1.6 times 10 to minus 19 square root of the whole stuff, and this is 6.63 times 10 to minus 34 over 2 pi. So we have E equals to 6.67 times 6.67 times 10 to 9 meter inverse. So the probability that the electron can go through would be simply exponential to minus 2BL. So we just substitute the stuff inside 2 times 6.67 times 10 to 9 times the thickness of it is 750 picometer, which is 10 to minus 12. So the probability that the electron can go through is 445 times 10 to minus 6, or it should be 4.5 times 10 to minus 5. It looks small, but actually there are many electrons. So if the number of electrons try to go through this wall is large enough, so there may be some electron that can really go through. It's something like when you try to buy Mark 6, if you buy one time, then you have high possibility that you cannot win the prize. But if you can buy it for billions of times, then you probably win the first prize. So the next one, approximately, this should be B, I think. This should be B. So here, what is the approximated probability that here we consider a proton rather than an electron, with the same total energy, 5.1 eV, transmitted through the barrier to appear and be detectable on the other side of barrier. So we just repeat the whole procedure. But here we use the mass of the proton rather than the electron, and actually UB and E is actually the same, times 10 to minus 19, and take the square roots, all over h bar 6.63 times 10 to minus 34 over 2 pi. So B is this time 2.86 times 10 to 11 meter inverse. So maybe one point I need to remember you is that exponential to something. So this term should be dimensionless. So we have minus 2BL. So 2 is dimensionless, and L is the thickness. So the unit of L should be meter. So the unit for B should be meter inverse. And likewise for other function like cosine something. Actually, radian is dimensionless, although we really need to write radian. But you can consider that cosine omega t or 2 pi ft. 2 pi is the radian, but it is dimensionless. F is hertz, t is s second. So in the dimension, they are inverse. So totally, inside the cosine function or sine function, it should be dimensionless. 就是在函数里面的 中间的东西是没有，整个是没有单位的，应该是没有的。In every kind of function, then it should be dimensionless. For example, this here is an exponential function or a cosine function. So likewise, we calculate the transmission coefficient, which is exponential to minus 2BL. So here we substitute minus 2 times 2.86 times 10 to 11. And the L is still 750 picometer, 10 to minus 12. So the answer is 8.3 times 10 to minus 187. So if you really want to write 0, 1, 0, 0, you have totally 186 zero before the 8. So this probability will be very, very low, which means that to have an electron with the same energy, it goes through this wall has a much higher probability. However, for a proton, the mass of it is 4 order larger, 3 to 4 order larger. For an electron, it is 9.11 times 10 to minus 31. So you can approximately write it as 10 to minus 30. And this one is around 10 to minus 27. So it is 1,000 times, more than 1,000 times heavier. However, the probability that it can go through the same potential wall is much, much lower. This is times 10 to minus 5. However, it is minus 10 to minus 187. I'm not sure whether you need to win the Mark 6 consecutive for how many times then you have this probability.